So now we're done, and so I think the point I want to make is that it's inconsistent to believe that the eternal black hole is smooth while single-sided black holes are not. Okay, so either the paradoxes apply to both settings or they apply to neither. Of course, I think that now, let me just build up for tomorrow's talk. This is important because we do have significant evidence that the eternal black hole is smooth. We do have many calculations that suggest that the eternal black hole has a nice interior which is empty and doesn't have any firewalls or anything else bad happening. And therefore it suggests that these paradoxes should have a resolution in the eternal black hole and also in the single-sided case. And that I will describe tomorrow. Okay? But I just want to say that whatever is true for the single-sided black hole is also true for the eternal black hole. So this is basically the end of my talk. Before so let me just recap and let me end with a few words. I started by talking about black holes, and the central question was, central point, something we know which is very robust from general relativity, is that black hole horizons about a big black hole look a lot like flat space. Now, and that suggests that you should be able to do effective field theory about black hole horizons, and Hawking and others did effective field theory about black hole horizons, and they seem to find some contradiction with unitarity, which is that they found that it looked like the black hole emitted exact black body radiation. But now we understand, actually we should always have understood, that this was not really a contradiction, because very small corrections can restore unitarity to Hawking radiation. So Hawking's calculation is not precise enough to lead to a paradox. Whether or not someone can do an e⁻s calculation, Hawking's calculation and all attempts at derivative analysis about a black hole are not precise enough to lead to a paradox. And then there have been attempts to try and fix the situation, to try and say that the information paradox is genuinely a paradox, and that these small corrections can't fix it. We started with this paradox with the strong subadditivity of entropy, but as I said, that can also be resolved if you recognize that locality is not exact in quantum gravity. But then there are these much better phrased paradoxes that are phrased in terms of low point or 2-point correlation functions in AdS CFT, and that are basically existence questions. And that's what I spend a lot of time talking about. And that also these paradoxes apply not just to large black holes in AdS, but also to the eternal black hole. So they apply to systems that are cherished, that we like a lot. So if I had to say, if I had to give you one takeaway, the point of this was to basically say what is the modern information paradox. I'll describe resolutions tomorrow, but I think this is an important thing which all of us should recognize. And the modern information paradox does not have to do with evaporating black holes and black holes leading to black body radiation, but rather it's a question of reconciling some robust properties of low point, bulk effective field theory Green's functions with very robust properties of the CFT, and it looks like we have a problem in doing that. And so this is one takeaway from the talk. Now I'll try and describe resolutions to these paradoxes tomorrow. Let me just end by talking about what is not a resolution. So I think that the firewall is not a resolution. And let me just tell you a little bit about what the firewall is. So the firewall is a statement that, because we found a problem in reconciling these, we should just give up the fact that these A operators exist, and we should just say that the black hole has no interior. If the black hole has no interior, then what happens to the black hole? We don't know, but why don't we declare that when you jump into the horizon, you're going up? So there's, it's really the statement of the firewall is that black hole has no interior, and if it has no interior, then there might be something bad, and you might die at the horizon. But I think the point is to recognize that this is completely giving up on effective field theory. And if you believe the firewall, then even the thermofield has these firewalls. The thermofield doesn't have a smooth horizon. That's a possibility. Or it's possible that the thermofield eternal black hole duality is ill-defined, and in fact, this is something that has been proposed by Manolf and Wald, and more recently by Samir Mathur and Borun Chaudhary and Stephen Areri. So some people have proposed this. But I think that we would like to not give up, and we would like to preserve effective field theory, and we would like to try harder to preserve effective field theory, and therefore the firewall says that you give up an effective field theory inside the horizon, or give up an effective field theory. And therefore, I'll try and talk tomorrow about how you can avoid the firewall and try and still preserve effective field theory. Okay, so this is all I have to say.
I have a question about the regime of validity for effective field theory. Is it supposed to be just a statement about low energy physics, or is it supposed to be about something where I'm not probing many states?
Both. It's supposed to be a statement about you need to limit the energy and also the number of insertions you have.
So So most of your discussion here, you were basically focusing on the former rather than the latter, correct?
Well, I was focusing on 2-point correlators and also correlators where you had, where the energy of the correlator was very low. These omegas could be like, Hawking energy, so the energy of order 1. So both these conditions are satisfied in everything I wrote.
Oh, I see, because you require that little n to be small.
I require that what's little n is the number of points, yes.
Yes.
I require little n to be small, and I require that, in the end I was talking about modes of a fixed energy. I was talking about these A omega and these A twiddle omega modes. And I will only demand these conditions be true for modes which don't have very high energy, which have energy of order 1 with the Hawking temperature. So both conditions are true.
What is the value of little n and what you would expect from
so
effective?
What is little n is
No, that wasn't my question. My question was, what is the value of little n at which you would expect the effective field theory computation to be?
So something which scales with n. I mean, you have to work out the precise power, probably n to the half. If you start putting in correlators which have insertions which scale with order n, then you expect the effective field theory will break down. Certainly not at little n equal to 2.
Yeah.
So if you take little n to scale with large n, as some power of large n, then you expect perturbation theory to break down. I think the correct estimate is n to the half, but
There's a general argument for that?
Yeah, the argument for that comes from, let's see. It basically comes from arguing, when the large n expansion breaks down. So the argument for that is, so you expect the bulk effective field theory holds as long as the large n expansion is good. And it's a question of counting number of Feynman diagrams and arguing, when the large n expansion breaks down. So let's see if I can get it now. There's some subtle factor ahead, but basically you look at an endpoint correlation function. This is endpoints. So all of these are endpoints. There's an n external point correlation function. You try and compute, scattering, and the number of Feynman diagrams that contributes to this at tree level is n factorial. And the coupling constant is 1 by n squared by n. So the naive estimate for this is n factorial to 1 by n squared to the n. This is the tree level. So just bulk perturbation theory. And then you can count the number of one-loop bulk diagrams that contribute to this. And the number of one-loop diagrams is actually up by a factor of. So now this is where I don't remember. But roughly it's you take a one-loop diagram of this kind, and you can break it up into p points and n minus p points. So number of one-loop diagrams that contributes to the same scattering process goes like sum of, this is p and it has p plus 2 points, it's p plus 2 factorial into n minus p plus 2 factorial sum over p. And each of these has 1 by n squared to the power n by n plus 2. And you can basically, so this is larger, it's larger by some factor of, it's n plus 2 factorial. So it's down by a factor of the coupling constant, which is capital N, but it's up by a factor of small n. And so when those two compete, at some point you get a breakdown. The exact point, I will have to be more careful about these factors. Actually, it's when n scales with you get a breakdown of the 1 over n expansion. You can see this from the boundary also, just to count, how many external insertions do you have to get a breakdown of the 1 over n expansion. That's where you expect bulk effective field theory to break down.
What would your answer have been if we were talking about the original phrasing of the Amps flat space, asymptotically flat space, where I don't have a notion of big N? I mean, I presume that the reason why you're talking about big N here is because the black hole is also big.
You can do the same thing actually for gravitron scattering, and you can see effective field theory breaks down for a large number of correlators. And the way big N enters is as follows. Let's say you have, so you're asking why does effective field theory break down if you try and measure, the entanglement entropy or something. So it's the same thing. The way big N enters is as follows. You see the dimension-less coupling constant that enters gravity is typical energy divided by Planck squared.
Yes.
So the typical energy, is in units of S is roughly 1 over S. Typical energy is 1 over S. So the dimension-less coupling constant that enters, scattering of particles which have Hawking size energy is 1 over S. And therefore, if you try to measure a capital S point correlator about a black hole with energy S, for that correlation function, so if you try to compute, so you might have thought that you don't have a big N in flat space, and therefore you can do things to arbitrary accuracy, but you can't because there's
well, obviously not. No.
Huh?
Yeah. bigger than that.
So if you're looking at correlators of modes which are much larger than the black hole, then surely you can have as many as you want before things break down.
That's right, but black hole is not emitting in those. You know, if you wanted to measure the entanglement entropy of the radiation outside, you'd have to measure a high quantum correlative with energies of the size of the black hole.
Right. So they just don't see anything
That's right.
interesting.
Other questions? Okay, so next time we speak again.
May I announce one thing? Tonight I'm planning the organizer of fund to cordially invite the Rome lecturers to one Taiwanese food restaurant somewhere in downtown.